Okay, this is the video lesson for Algebra 1, section 7.7, exponential growth and decay. So here we're just going to model exponential growth and decay. So starting with a model, an exponential growth is basically when your variable is in the exponent. So the exponent in this case is x, and here we can zoom in. And you can see the exponent is our variable, and so a is going to be a number. It's in the initial amount, what you're starting with, and then when x is 0. This is what you're going to start with. And then the base is the number that has the exponent on it. This is going to be, if it's greater than 1, it's called a growth factor. Okay, so we'll just start with it being a growth factor. If it's in between 0 and 1, then it's a decay factor. That means it's going down. So in this case, we'll start with growth, exponential growth. This is when the base is greater than 1. And this is what the graph looks like. As x gets bigger, this thing just shoots up and goes high so fast because the exponent is what's changing. So let's see what the first problem says. Since 2005, the amount of money spent in restaurants in the U.S. has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. If this trend continues, about how much will be spent at restaurants in 2015? Okay, so this is saying, let's get our formula here. Y equals a times b to the x. So our initial amount, when x is 0, that's going to be, in this case, what we're starting with. The initial amount here is 360 billion. So y equals 3, and let's just do this in billions. So we'll use 360. And then this, the money spent has increased about 7%. So that means if this increases by 7% is that, and then you have a 1 plus the percentage. So that means this is going to grow 1.07 every year. And so x is going to be years. Okay, so if we did it for 2 years, right, it'd be 360 times 1.07 times 1.07. And you basically multiply by 1.07 every year, right, because that's the growth is going to continue. And so that's where the exponent comes in. In this case, it's saying the initial is 2005, so in 2015, it's 10 more years. So this is basically asking, what is this y when x equals 10? So we're going to do 360 times 1.07 to the 10th. And we get about 708. And remember, this is billion. And this is dollars. So in 10 years, they're expecting $708 billion will be spent in restaurants in 2015. Okay? Okay, and then just a note about this growth factor here. Right, the reason this isn't just 0.07 is because you're adding 0.07 to what you already have. So if you multiply by 1, right, you would keep all the people you already had, and it would be the same, but then you're adding 7% of that. So that's why the growth factor is 1 plus 0.07, or 1.07. The 1 stands for everyone stays the same, and then we add this much more. Okay, so use that for this problem here. Same thing, but population of a town. And then here's its growth rate. So figure out what its growth factor is, and then figure out the amount of time between these two, and that will be your exponent. Okay, press pause and try this on your own and check back for the solution. Okay, so we get about 36,274 people. So here's our exponential function, or our exponential growth. Our initial amount is the 25,000 people. Our growth factor is going to be 1, the amount of people we started with, and then we're adding on 1.5% of that. So our growth factor is 1.015, and then 2025 minus 2,000 is 25 years. They want to know what's the new population after 25 years. We put that in the exponent and use a calculator to get that many people. Okay, now moving on to compound interest. That's an exponential growth function, and this is the formula for it. You do not have to memorize this. I will give it to you. But here's all the pieces. The P, A is going to be the balance. That's the total amount of money you have. P is the principal. That's what you initially start with, your initial deposit. R is going to be your annual interest rate expressed as a decimal. And then N is the number of times interest is compounded per year. And then T is the number of years. So it's sort of what we just did, but we have this little n in here. And that's because if it's compounded 2 times a year, right, then you'll divide your rate by 2, and then you'll double your amount of times you get it. That's because this is an annual interest rate. Okay, so suppose when your friend is born, your parents deposited, let's write this formula down first. 1 plus r over n to the nt. Okay, so our initial amount is 2,000, that's our p. This is my r, except it's as a decimal, 0.045. And then this is quarterly, so that means my n is going to be 4. That means 4 times a year interest is compounded. So then what is the account balance after 18 years? So t is 18. So let's plug that all in. A equals 2,000. 1 plus 0.045 divided by 4 to the 4 times 18. And then put this in your calculator or Desmos, and you get $4,475.53. Okay, and then this one for you to try, it's the same exact thing, but now this is compounded monthly. So what does that change here, right? This was compounded quarterly, now this is monthly. So see if you can figure out what changes about this, make that change, do the calculation, and see what the account would be after 18 years if it was compounded monthly instead of quarterly. Press pause and then check back for the solution. Okay, and you can see you get slightly more money, 4,489.01. After 18 years, it's just not much more. And we'll have much more to explore, many more sections to explore that when you get to Algebra 2 and pre-calculus and above. Okay, now we're moving on to exponential decay. So it's the same exact thing, except the base now is a number between 0 and 1. It's not going to be bigger than 1. So that means it's going to be going down. As x gets bigger, as time goes on, it's decaying instead of growing. Okay, so let's see a problem with that. We're going to do it the same exact way, just our base is going to be lower. Things are getting smaller instead of getting bigger. So the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases about 11.5%. What is the approximate pressure at an altitude of 3,000 meters? Okay, so let's start with the same model, y equals a times b to the x. Our initial pressure, so this is pressure. Our initial pressure is 101, so this is our A. Our B is our decay factor. It's going to decrease 11.5%. So remember before, when we were doing population growing, we had 1 plus, and we'd add on a percentage. Here we're actually going to subtract. So our decay factor is going to be 1. We have what we have, but then we subtract what we're losing. And this is a decimal point, not 0.115. So our decay factor is 1 minus 0.115, which is 0.885. Okay, so that's our B, 0.885. And then our X, this is saying for every 1,000 meter increase in altitude, the pressure decreases about 11.5. So this is when X equals 0. If we go up 1,000, that would be 1. 2,000, 3,000, that would be 1, 2, 3. So we're going up 3,000 meters, so each one of these 1,000s counts as 1. So 1,000 goes 1, 2,000 is 2, 3,000 is 3. So we're going to put a 3 here. And then we'll put 101 times 0.885 to the third power, and we get about 70. And that is a kilopascal. So it's about 70 kilopascals. Okay, so try this one again, but now it's at 5,000 meters instead of 3,000 meters. How does that change this problem? Press pause, see if you can figure that out. Try it on your own, and then check back for the solution. Okay, and so what that changed was just the, since it's going to 5,000 meters, that goes up to 1,000 5 times. Goes up 1,000 5 times. So our X is 5, and that changes to 54.8 kilopascals. Okay. And that's it. Enjoy.